supposed to give people a minute, or?
Let's stay on track.
Okay. All right. Ooh, that's more sensitive than I thought it was going to be. Great to be here with y'all. Great to, it's nothing like being the first presentation in a day like this, because you never know like what the vibe is going to be. And so like if you're like, end up thinking like, wow, these guys have no idea what they're talking about, that's fine. Just, share it somewhere else. Wes and I are here to talk a little bit about some of the sources of bias, specifically missingness in data. And talk about what our process has been to work in an interprofessional, interdisciplinary capacity to address that. A little bit of disclosure. So we work for the Critical Path Institute, which is a public-private partnership with the U.S. Food and Drug Administration. We specifically work with drug developers, industry, academic, patient advocates to work in a pre-competitive space on drug development tools, and that includes biomarkers, clinical endpoints, algorithms, and all the other mechanisms that go into developing a clinical trial for submission to the FDA. But all of that is to say, this presentation is our opinions, not an endorsement by the federal government. So please don't take it that way. I think we'll also have a mechanism to make our slides available for people who want to look at them afterwards. We are going to be using Slido. We'll talk in just a minute, but we weren't able to have our full data set available for y'all. And we'll put this QR code back up each time we ask you to interact. And hopefully I'll be able to figure out how to go kind of seamlessly back and forth between the slides and Slido. But we'll ask you a few questions throughout. I want y'all to participate. If you have access to our data, we'll show you where the data path is, and you can we'll follow along with some activities. If you're having any trouble, don't worry. We will show you the answers as well when we go through this. So I'm going to let Wes introduce himself.
Awesome. Yeah. Hey, everyone. Glad this microphone's working. So I met Group 4 a second ago, but yeah, I'm Wesley Anderson. I'm a quantitative medicine scientist here at the Critical Path Institute. Graduate training degree is technically biomedical engineering, but I had a heavy focus on machine learning. And yeah, great to be with you all today.
And I am CPATH Senior Scientific Director for Real World Evidence. My background is in nursing, specifically emergency room nursing, so I know enough about critical care to be dangerous and annoying, but I'm certainly not the clinical expert. And my graduate training was in public health, specifically evaluation science, actually at Clemson. And Jay and I ran into each other a couple of times. We'll see if he actually remembers me or not. I was just a first year, I think, when I interacted with him. But you've got our emails on these slides, as well as QR codes to get to our LinkedIns if you want to connect. And we'll be happy to put this information back up later as well. So the conversations this morning were about building community. And so we wanted to talk just a little bit about our approach at CPATH. One of the wonderful things about CPATH is that we're kind of a flat matrix. So regardless of kind of our title, we all end up working in a much more collaborative space. That lets us be a lot more transparent and engaged with each other. And operate inside of a growth mindset where we each kind of have our little area of expertise that we own, that we work on, that we speak from, but we're also leveraging each other's expertise. So as Wes and I work together, there's frequently times where I am staring at him blankly as he's trying to explain some machine learning concept because I did not do a quantitative degree. But he lets me ask my questions and I'm able to better understand. Then I can bring a clinical perspective that helps inform the model, helps us think more carefully about making sure we're specifying everything correctly and making sure we're not introducing additional bias, because we know real world data is messy as it is. And part of that is learning from our mistakes. There are always going to be mistakes, whether that's me as a leader making kind of the wrong call on an analysis, and at the end we kind of have to scramble to fix it. That's something that happened in a causal inference paper recently. I made a wrong decision a couple months ago, and now the whole team's having to scramble. Or if something has gotten in the code wrong, it's really important that we talk through it and talk about the implications and think about all the ways that we need to fix that throughout the whole project. If you don't have this kind of working environment, you end up living in a silo, and you're not learning, but you're also not helping other people learn. Each of us in this room has a slightly different background. Is anybody else in here a clinical background? Okay. And who here is like pure like computer science data? Okay. How many of y'all kind of live in between, have formal training in both, right? And so even those of us that have some training in both, you're never going to be the master of all things. You can be a jack of all trades and a master of none, certainly. But it's important to work in that collaborative environment. Anything you want to add?
Yeah, no, the number of times I've pretended to be a clinician very briefly and then realized I didn't know what I was talking about. I had to run a SMITty to clarify things. Yeah, absolutely. So the collaboration is probably the most important part.
Yeah, and so we're specifically going to talk through an example of this where we had to learn from each other today. But the most important mantra is that we kind of remind ourselves that we're saving PDFs, not lives. And that's not to trivialize what we're doing as data scientists, as researchers, but it's a reminder that, for those of us that are in a clinical environment, you've been in a situation where you have a finite amount of time to make a decision to potentially save someone's life. That's not the case in research. What I always want to remind ourselves of is the worst case scenario, worse than getting fired, worse than losing the grant, worse than your company shutting down. The worst case scenario, in my opinion, is you publish bad science, because that's how we end up hurting people from this perspective. And so it's really important to take our time, work through things. Datathons are great exercises for us to rapidly think through these processes, but we know in the real world we need to take time, sit, and think through each piece. We have the real luxury at CPATH of not being an academic institution. I have faculty appointments, but I'm not like tenure track, so that publish or perish mindset doesn't impact us. So it's also really easy for us to talk about this. But the advice I would give any young researcher is take your time, and keep in mind that that is the worst case scenario, is that you publish bad science that hurts someone. It's not actually the worst case scenario that you don't get the grant. Okay, so a little bit of background about how our specific project came into being. How many of y'all are familiar with drug development processes and frameworks, the FDA? See one or two hands up. Okay, so FDA is this giant monolith that tries to make sure our drugs are safe. Does anybody know about thalidomide back in the day? Yeah, so basically the entire FDA can be explained by thalidomide. Thalidomide was a drug that was made available for nausea and pregnancy, caused horrific birth defects, right? And absolutely terrifying time in medicine, in healthcare, and the entirety of FDA is structured to make sure that never happens again. And that's the important thing to remember. The product of that is we have a very specifically designed system that incentivizes the development of new products over the expansion of the existing products. We have about 10,000 conditions that are documented in like the ICD codes, and only 2,500 drugs. So there's upwards of 70% of conditions have no FDA-approved treatment. Many of those, of course, are rare and ultra-rare conditions which pose their own challenges to drug development. Our project and our team was set up with this in mind to think about how do we leverage real-world data to make drug repurposing more practical. And it's also a big issue because you all know about patents and exclusivity. There's kind of a finite window when it makes sense for a drug company to expand the label. If you're following the GPL1s, the semaglutides, they're getting the labels expanded over and over and over again, but that's because they're right in this early phase. There's only a certain number of years that the pharmaceutical company will have exclusivity on that drug, and that's when it makes sense for them, that's when they can recoup their expense for expanding that label, because it costs money every time they submit new data to the FDA. So things that are way out there, that are totally generic, like aspirin, is used for all kinds of other things, but will probably never get the label updated because no one has a financial incentive. More about drug repurposing. Does anybody know the FDA's guidance on real-world data? Anybody read it? No? Really? It's such light, wonderful reading. It's only like, I have a stack on my desk at home that's about this thick, because there's like 18 guidances out now. The big thing that you need to remember is that, yes, the gold standard is a randomized controlled trial, but an RCT can't work in every scenario. There are situations where there's either not enough patients or there is an ethical issue with doing an RCT. For example, if something has become the standard of care, one of the things that I think about is anticoagulants. The directed oral anticoagulants like Coumadin and warfarin are all labeled for venous thrombosis, for a blood clot in your veins, but they're all also used for arterial. But in order to do an actual RCT, you'd have to withhold that treatment from a patient, where you know that's probably the best thing that you can give them. So that's called a loss of equipoise. And you end up with this situation where you can't ever actually conduct an RCT. This happens especially in vulnerable populations, in children, and pregnant women. And this is where we can start using real-world data. Through causal inference methodologies, through machine learning, we can build mechanisms that help us make some kind of guess or educated guess about the true efficacy of a product based on an effectiveness study. There are, as I said, there are hundreds of pages of information. There's a few key summary documents that are really important to read. But the thing that I really point people to is this figure. The FDA would encourage us to think about a few things. One, is the completeness of the data appropriate? Is the population represented in what we're looking at? But the thing that we're going to talk about today is understanding what influences might impact what data is actually missing and that full context. Because this is the real world, right? A patient comes into the hospital or into the doctor's office. There are some tests that we kind of standardized do on patients, but we don't do all of it, right? So there's going to be data missing based on the clinical practice. And so it's definitely not missing at random, and we need to think about that really carefully as we move through any analysis leveraging real-world data. So we were part of a team called the Cure Drug Repurposing Collaboratory, which is now sunsetting, just transitioning into other teams. And you can see we had funding to do a pilot project in COVID-19, because of course it was 2020, and that's what everyone cared about back then. COVID is not that sexy anymore. So the analysis that we're going to talk through with you today is really much more about advancing the methods of using machine learning on real-world data as opposed to the impact they would have on evidence for clinical practice around COVID-19. This was a $9.2 million grant over 2 years. It started in June 2021. You can see our list of partners. Emory University was a primary institutional partner, and we're very thankful for them. They were able to make some of their data available for y'all for this week. But we obviously couldn't make the whole data set available due to some licensing issues. Our full data set is fully specified under the OMOP pre-configured rule system or common data model. There are 160,000 patients represented in 18 healthcare systems. It is the index hospitalization for acute COVID-19 among all those patients. We do have a process for individual researchers that want to access the data for specific projects, and we are happy to work through, get that approved, get it licensed. Judy always knows how to find me. She made sure she had my phone number. She knows where I live. Like, I can't hide from her. Yeah. Well, she knows my mother's maiden name, like everything. So anybody that wants to see the full data, get access to that data, we want to make it available. Those of you that were at the SCCM Datathon, you got to have a little taste of it. But as Judy was talking about, it's really important to see other data sets. We'll talk about the specifics a little bit more, but the big thing with OMOP is that it's supposed to retain the full granularity. There's a lot of nuance, and we'll talk about some of those in the beginning, but when you look at an OMOP data set, you think, oh my God. Actually, my first conversation with Judy, I am standing waiting for the bus, and she walks up and says, your data set is messy. That's how our friendship started. But we have a cleaned up analysis data set available that you can look at. There's the path for it right there. Wes, anything you want to add before we start talking about COVID?
No, I think we're going to get into a lot of the intricacies of the data as we go through this. So no, I think we're
okay. So we have a couple clinicians in the room, and some of you are going to roll your eyes, and you're going to think this is oversimplified. But bear with me, okay? There's a reason. So SARS-CoV-2, the virus, does not kill people. Right? Does everybody know that? Does that make sense? That's not what actually happens. It's an inflammatory process. COVID-19 is a syndrome. There's an inflammatory process that happens like with any infection. And it's when that inflammatory process gets out of control that we actually start having problems. Right? Does that make sense? Everybody with me? Okay. So we try to measure that through proxy measures. We're not actually measuring it directly. We are looking at this. But there's also patterns to why these are available. In the general COVID population, if you had patients that weren't hospitalized, you might have a couple of vital signs. You might have a heart rate, you might have a respiratory rate. You're not going to have a lot of labs. You're not going to have documentation of what their oxygen needs were, because it's not going to be, it wasn't in the hospital. So that there's already one level of missingness that is based on the clinical progression. So we try to do our best to measure these, but we are always approximating in research. I'm going to ask Wes to talk a little bit about the full power of OMOP as we start thinking about how all of this ends up being represented.
Yeah, so for those of you that may or may not be familiar with OMOP, I guess I can get a little hand raised. Who is familiar with the OMOP common data model? A few hands, awesome. Yeah, so it is basically a pre-configured rule system, as Smitty said, that includes a number of different standardized vocabularies. And the idea here is to take all of the disparate EHR systems, Epic, Cerner, among others, and to get them all into a standardized set of vocabularies that can then represent the full granularity of the patient's interaction with a healthcare system. So that can look like across time, all of the measurements that were taken, all of the different procedures that the patient may have underwent, the drugs that they were administered, and then the conditions that were either pre-identified prior to the visit that we're talking about or are identified during the specific visit. And that can include not just the comorbidities, but the specific disease that they've been diagnosed with that is the focus of their healthcare interaction, and then the outcome that may or may not have occurred during that time. So this, I think, is a good way to look at the data as we're walking through. What we'll be speaking to is kind of put yourself in the shoes of someone that is interacting with the healthcare system and what may happen as that interaction is happening, and all of the different ways that a clinician will be estimating what is going on inside your body, like Smitty was saying. So, and something that was a major part of our project was the ability to take the tools that the Odyssey community, which is the community that has developed and is maintaining the OMOP common data model, across the process of getting data from those disparate EHR systems into an analysis-ready data set. And that includes extracting the data from the different EHR systems, transforming it into the common data model, and then loading it into said model, along with determining the data quality after that's happened, and then finally being ready to analyze it. And this Docker deployment that we constructed through Microsoft Azure allows for these different tools to be used, not just within the larger community healthcare systems that may have had the resources prior, but now can be used for communities with various resources. And yeah, I guess extends the ability to collect more data over time. So I think something else that's really important to talk about is how we can actually get to the analysis data set from what comes out of the EHR. So what we have here is a list of a number of the sites that we were able to partner with to get data from those EHR systems into the OMOP common data model. So something that we started with once we received that data in the OMOP form was looking at not just data quality as we normally think about it, any extraneous values or missingness, but also almost validating the data set specific to the condition that we're looking at. So COVID-19 has some things that we would think should be present, like the example we'll give here is that does the number of patients reported having been on a ventilator make sense clinically? If we have a healthcare system that has around 7,500 patients, you wouldn't expect there to only be 12 patients that had been administered a ventilator at any point. So that would be something that we could flag as not necessarily making sense. And another important step there is not just looking at what happens within the healthcare interaction, but also when does it really start and when does it really end? And that can be something that is determined not off of specifically a start and end date that's provided in one of the OMOP tables, the visit table, but also when do records actually start being taken? So when is the patient's first measurement taken, whether that be a vital sign or some sort of blood measure? When was the first drug administered, that sort of thing. So these dates can be aligned across the common data model to make sure that we really understand the beginning and the ending of what we'll be analyzing. And then finally, looking at across the different components of the healthcare visit, the measurements, again, the drugs, the devices, can we find all of the relevant ones that we're interested in? And there's an example here on the next slide. But making sure that through the OMOP hierarchy, which includes what we call parent concepts that are relative to a larger set of terms, and then child or descendant concepts. So an example of that will hopefully make sense. So what we wanted to look at in one of our analyses for causal inference was the use of dexamethasone within the inpatient setting. So to be able to find all the different examples of dexamethasone within our data, we would use the parent concept of dexamethasone, which for the OMOP common data model is it is an ingredient concept, and then using the hierarchy, we could get this full list of all of the different forms of dexamethasone within our data. So what that looks like is a number of different oral tablets that we saw, along with some ophthalmolic solutions and some injectable and oral solutions. So there's a lot of different forms, and something important here is to look at which of these are actually administrations that we're interested in analyzing, and which of these don't make sense towards the actual treatment of COVID-19. And The ones highlighted in green here were actually ones that we removed because they are not, relative to COVID. And there's also the ingredient at the top here. So another important thing to determine is when just looking at the representation through the ingredient, is that actually the tablet or injection or IV administration that we would be interested in, or is that something else that is being looked at? So another important consideration when setting up your analysis data set. And what this all kind of came to is knowing that COVID is a very heterogeneous disease where you could have, or it can range from whether it's in the clinical setting or outside of the clinical setting, asymptomatic patients all the way to patients that experience mortality. So even within the inpatient setting, we know that COVID can be, again, very, very heterogeneous. So using unsupervised machine learning methods, we can look at all of the different data that we have within our data set, including demographics, the different lab measures, whether they be blood chemistry tests, routine blood tests, different levels of oxygen administration, and comorbidities that may be present within our patients. And can we find patterns of disease severity and use that to determine the prognosis of a patient by just looking at what happens within the first couple days of hospitalization. So that's what we looked to do here. And it's important to note that this is the analysis that we wanted, and this is leading into kind of the missingness that we're going to talk about. Some of these measures, as Smitty's been saying, aren't necessarily routinely looked at. So determining what can actually be included based off of what is available versus what isn't available for various reasons is something that we'll be talking about.
Yeah, so a little bit of Slido exercise. We're going to ask y'all to log into Slido and tell us what, oh, that's the last question. I gave it away, didn't I? Yeah, this one. Remember I said I wanted to see if I could do it smooth? Everyone just pretend that was really smooth and efficient, okay? So, Lord have mercy. So, give us your thoughts. Let's throw some thoughts in there. How would y'all approach this? We've got a clustering analysis. We know there's some data missingness. What are some of your initial questions? What are the things you want to look at as you start exploring this data? What big concerns do you have at this point about this kind of project? And if people want to call stuff out too, that's fine. We just wanted to give it an anonymous platform, but this room is small enough. Any thoughts? Randomness of missingness, distribution, imputation without bias. Oh, we're going to go there. Hidden confounders. Yeah. Okay. So y'all are thinking about this kind of very similar to how we thought about it. How to ethically remove the data that seems not complete. I like that answer. Decide your parent cohort. Use of synthetic data to fill in the missingness. Oh, that's a whole fun conversation. In the interest of time, I'm going to pull this back over and we'll start talking a little bit. So the inflammatory response is the primary driver for how COVID kills you. For those patients that are more severe, however, there's also microvascular clotting. And there are certainly lots of ways to measure this, but we don't capture this data on every patient. And those of you that are clinical probably already know where I'm going. But one of the tests that we use is a D-dimer. And we're specifically going to talk about D-dimer for this exercise. There are other measures that are important, some of the inflammatory markers, LDH, CRP, sed rate. And we also don't collect those on every patient. But we're specifically going to talk about D-dimer as an example of how we can bias a model without thinking through the whole question. So knowing that we think there's some patterns of missingness that are probably not at random, knowing that we have some concerns, we were going to ask you to explore the data, but in the interest of time, I think we might just show you. what it looks like. And so we're specifically going to focus in on D-dimer a little bit. I'm going to let Wes talk a little bit. We've got a couple figures of some of the other measures as well. But talk a little bit about what you saw in the missingness.
Yeah, so the way that we thought about this was to look at overall missingness of all the different indications that we wanted to use within that unsupervised machine learning method. And these are all predictive of, or have been shown previously to be predictive of COVID-19 mortality. So looking at what can be included and what can't, something you'll see here is that overall there is a clear distribution of these measures where I guess the skew is towards the left, but you can see that there are extraneous values that are clinically meaningful in the sense that someone with a higher D-dimer, higher LDH, higher C-reactive protein are likely to be in a more severe disease state. So looking at this in terms of all the values in our data set that we provided, as I think a few of you said, it may be important to break them down into different ways to look at disease severity, whether that be mortality or another indication. So what we did first is looked at a breakdown of alive versus deceased, not just to look at how the distributions vary across those different patient groups, but also how the missingness changes. And I guess I didn't include percentages here. What we can see is that there's a clear trend towards higher values in the patients that are deceased, but also if there were to be percentages here, there is a lower amount of missingness for those that ended up being deceased versus those that survived their hospital interaction. So that's an important first look, but it may be also valuable to look at another way to break down disease severity, which is another thing we did, and I think it's a few slides ahead. But
so how are the imputation folks feeling? You still feeling confident about an imputation approach?
Overall,
Anybody?
the missingness. Oh, sorry.
Sorry, go ahead.
Overall, the missingness for D-dimer specifically is 20% in our data set.
In the data set we shared.
In the data set that we shared, yes.
It's much, much worse in the full data set.
Yes.
We'll have that. So part of what's going on is what data is available is driven by physicians and nurses' perception of how severely ill this patient is. And yes, we all know that. That's something we think about all the time. But if we don't specifically stop and think for a complex analysis like this, we're going to miss it. And we're specifically call out D-dimer because of some of the nuances around it. So let's see if we can do another slide. Let's do a quick vote. Based on what you've seen, I'm giving you three choices. An imputation approach, dealing with the missingness, whether that's imputing based on means, normal values, nulls, whatever, versus complete case analysis, omit the D-dimer from the model altogether. Those are the three choices that we're going to think about. Great question. So complete case analysis is where we only analyze those patients that have all of the data available. So if they were missing D-dimer, if they were missing LDH, we exclude them from the model. I love that their thought process followed exactly what our thought process was. Yeah. So the winner far and away right now is complete case analysis. And I think that makes sense. Definitely want to talk about imputation and omitting as well. So the next thing we started to do was to look at D-dimer by another proxy of severity, whether the patient required oxygen, only had some other oxygen up to invasive mechanical ventilation, and then the invasive mechanical ventilation by themselves. What did you see, Wes?
Yeah, so surprisingly, there was actually a little bit more missingness for patients that survived and that were deceased and didn't require oxygen. But overall, you can see that there was a clear trend of lowered missingness as oxygen supply increased. You can see here at the bottom, one of the values is covered up, but there's about 18% missing for patients that were alive with didn't require oxygen. I believe it's in the mid 30, or what is that number? And 15% for ventilation, whereas when you move to the patients that are deceased, if you want to, higher missingness for patients that ended up passing away in the hospital setting that didn't require oxygen, but lower missingness for those that were deceased and required either oxygen support up to mechanical ventilation or mechanical ventilation. So there is a clear trend towards this measure being taken for those, not just that are have a potentially have a poor prognosis, but also require a high level of oxygen support at admission.
All right, one of my clinical peep. What is a D-dimer used for? Pulmonary embolism. Does everybody know what a pulmonary embolism is? Big blood clot in the lung. It's bad news bears. It's the stuff that ER people have nightmares about. But that's the test that we use. There's a lot of things that can make it elevated. It's a sensitive test, but not very specific. Any inflammatory process is going to make it elevated. However, if we test someone, if we run their D-dimer and it's positive, we then have to deal with that. We have to go and do a CT angiogram, which not only is potentially toxic to the kidneys, it's additional cost, exposure for the patient, choose a resource for the health system. So it may not actually give us the information that we want for every patient, but it may create additional issues and specifically might generate some liability for us as providers, for the hospital. So specifically for D-dimer, there is a whole ecosystem of factors that determine whether it's actually available or not. And so we had a deep discussion about whether we could do a complete case analysis because A, the objective was to look at all hospitalized patients, not just those that were severely ill. But B, not only is it not missing at random, it's missing due to some very specific constraints in the US healthcare system and the way our system functions. And so we made some decisions, and again, like the data that you saw was specifically for the Emory data set we show you, which Emory was actually one of the better data sets. It was amazing. They're a wonderful group to work with, fantastic, but a lot of other sites either didn't have. There's always cultural differences between health systems, but some sites weren't able to extract data at the quality that Emory was. So Wes, what did we actually do?
Yeah, so I'm actually going to go through this pretty quickly because I think we're about at 5 minutes left. But what we ended up doing was removing those variables with significant missingness, including D-dimer along with C-reactive protein and lactate dehydrogenase. Although they were shown to be strong predictors of COVID-19 mortality, I believe they're missingness across all of our different sites, where it's about 50%. So there's not a lot that we could do there, at least in the time being. There may be some things to counteract that as we move forward, but as this initial analysis. And what we did overall is we performed factor analysis of mixed data, which is basically a principal component-based method that reduces the dimensionality of our data to improve the performance of clustering, and used a hierarchical clustering method to look at if there were any patterns of severity across our different patients. We used a few different tools in the middle here, like determining the optimal number of clusters within our patient groups. And then once we found these clusters, we looked to both statistically analyze the different components of the data, including those blood chemistry, blood tests, coagulation functions, as well as comorbidity, oxygen support, and then the treatment strategies, and then look at the differences in survival across our groups. And then at the end, we actually trained a few classification models to determine if we could see which patients belong to which group, as kind of a validation of what we found. And this is a quick visualization of the hierarchical clustering. For those of you who aren't familiar with it, it's kind of a bottom-up approach where you can start with all patients being in their own groups, and then over time group them with other similar patients. And as you move up the hierarchy, the groups become smaller, and at a certain point there becomes an optimal number of these groups, and that can be determined by the distances within this hierarchy, and also a number of different analysis of the clusters. So a specific package in R was what we used to determine the optimal number, which you can see on the graph here on the right ended up being 3 groups. So next slide. And then from that, we looked at differences in our continuous and categorical variables to see was there differences in age, those different blood measures, as well as categorically the comorbidities, levels of oxygen support, and how the patients were treated in terms of COVID-related treatments. And as you can see, we'll see which groups are more severe here. There's definitely a more severe group, and then two clusters that ended up in terms of their survival being not statistically significantly different, but they definitely had differences in their clinical features, along with differences in the length of time that they spent within the hospital setting. And then trained 3 different classification models at the end to see, can we take these patients and actually place them into the groups based off of these clinical features, and had strong performance from our classification models in terms of common metrics for machine learning, precision, recall, and F1 score. So yeah, kind of validated that what we found made sense, not just in a clinical sense, but also statistically and through some of our other supervised machine learning methods. So
yeah. So our last couple slides are reviewing some of the other stuff, so I'm gonna skip that. I wanna ask y'all, what do you think of our approach? Basically, how bad do you think this peer review is gonna be, is what we're asking. You know, it's always rough. Oh, we got some skepticism. Oh. One person thinks, a couple people think we did really bad. So at the end of the day, how we approach these, yes, there are some rules, yes, there are some guidances, but at the end of the day, we kind of have to make a judgment, right? We have to make a subjective decision about how we model this, and we have to defend that decision. The deeper we can get into understanding where the data came from, what it might mean for something to be missing, what might drive patients, providers, nurses to document, not document, share certain things, the better decisions we can make. And so as we draft our paper, our limitation section is getting really long, but feeling like trying to make the decision of have we fully exhausted looking through all the different ways to do this? Can we do a sensitivity analysis and do a complete case analysis on a certain group? Looking back, and can we look at how the D-dimer was actually distributed across these clusters, and does that give us any sense of how valid the original model was? All of these are part of our decision-making process. And as you can see in this room, the majority of you are kind of not sure whether we did a good job or not. And I think probably any paper, any publication, you're going to have mixed reviews on. I think that's the most important thing to keep in mind. But if you have a strong team, and if you're working closely together and you're learning from each other, your ability to construct a more defensible model and make more defensible decisions is going to go up, no matter what you're working on. I think we're at time, but we'll make our slides available, and y'all can connect with us elsewhere. We hope you'll have a wonderful week here at the Datathon, and thank you, Judy.
Awesome. Thank you. So another round of applause, please. So we're going to put the slides. First of all, any questions? No? Okay. So, yes, Marianne?
Pressure. So coming from a clinical background, I guess the question, to me, it looks like a large problem is how the provider, the clinician is thinking and how they document. And so how are we gonna get that better? I mean, I'm guilty of it. There are times you just write 2 lines and you know what you mean and you know what it means to you, but if somebody else, a third party, is trying to use that information, how do you crystallize it and turn it into a data set like what you have? I don't know. I'm just curious.
No, exactly right. So you heard the mantra garbage in, garbage out. We, for years, have thought of the EHR as being a bad data source. But the reality is we need it, right? And so it's not a question of is this a bad data source or a good data source. It's can we develop methods to account for all of these mechanisms. And so when we are working with the FDA, building these processes, trying to explore how to do this, we focus on whether we think we can fully explain all of the different factors that might contribute to whether something is or is not documented, is or is not ordered. In rare disease, it's also complicated because there may not be a diagnosis code, so you may have erroneous diagnosis codes to help get an imaging test covered by their insurance. There's so much messiness in the EHR, and it requires that perspective. And so being the clinician on the team, my role is frequently to try to explain, okay, here's what the nurse is going through, what they're thinking through as they're documenting on this patient. Here's what the process actually looks like when you're bringing a trauma in. And so we can think about why some of that data might be missing and see, is it ultimately a fatal threat to the analysis at hand? And if not, can we acknowledge enough limitations, put enough asterisks for this to still be meaningful without being completely laughable? But you're absolutely right. But it all comes down to interdisciplinary work and making sure you have a clinician from the specialty as part of the conversation, I think.
Yes.
This is just a comment, just like as we're going forward. It was a little hard to see some of the titles on the axes. So if we could maybe share like the slides while we're going through it, that would make it a little easier.
That's an excellent point. Thank you.
Slack will be where, oh, no, Wes already showed us where all the material will be, but that's a great idea to just share the content and people can watch as we go along. Any other, yes?
With the last example you gave us with DEXA, what was the challenge you had when you were de-anonymizing some of the data at first? So having the balance between, for example, working with pediatric group, how do you manage HPI and then again de-anonymize and then make sure also?
Yeah. So this data was fully de-identified by 45 CFR standards. We used masked patient identifiers, so like a randomly generated patient identification number, and we used a shift and truncate algorithm to shift all the dates in the chart by up to 6 months in either direction. That retains the temporality, so the distance between date of birth, date of admission, date of discharge is the same as the real data, but we don't know the precise data within a year, and that's a HIPAA definition for de-identification. So it's not fully anonymized because, you know, with like 20 data points, you can identify someone essentially in a chart. But it's de-identified. We did have issues. Some healthcare institutions didn't want to submit pediatric data specifically because of that concern. Their IRBs wouldn't approve it. It is a big challenge going forward, and that's where some federated approaches come in. It's probably a little bit out of the scope of this data-thon, but yeah, it's a big problem.
Okay, so you know, one of the things that Smith and Wesley represent is this pair of computer scientists and you know, clinical expertise, right? So maybe a comment about how you merge those together, because it's very rare, and you know, it's just so rare to. Some of these things look easy when you present that, you know, that map. Like, okay, look, we are looking at what are the markers of inflammation, right? How do you sort of improve communication? What are the skills that are necessary to be able to do that sort of interdisciplinary work?
We sing Taylor Swift songs and drink beer. It's having a relationship where we can be blunt and transparent with each other and acknowledge, you know, I get to the point where I can say to Wes, I have no idea what you're saying. You know, frequently in our conversations, I have to say, wait a minute, I don't know what's happening statistically anymore. And Wes, similarly, we had to get comfortable enough where Wes can come to me and say, hey, the physicians keep using this word, and I don't know what it means. And we'll talk through it, or what does this lab value mean, or what does this range mean? But we had one example where someone submitted their weights in ounces, and it took us like a week to figure out what was happening because we didn't have a unit with it, but it took both of us kind of digging through it and talking to people and being vulnerable and being willing to someone think we're silly in order to actually understand what's happening. What'd you add?
Yeah, I think that and the number of times it took somebody to go through different white blood cell and red blood cell counts and actually remembering what was what. Probably still don't have all of them memorized, but we're getting there. So yeah, just being, like you said, right. Being vulnerable and being willing to show everything at some point, at least, to say this is everything we have. Where do we go from here to really have that communication go forward? So.
And I'll just add one more point. You know, Judy and I have had a lot of students come through the lab with different levels of expertise over the past 5 or 6 years. The one thing that makes students stand out and really contributes to their success is, especially if you're not from a clinical background, just computer science, for example, is that willingness to actually try to learn the clinical domain, right? And there's never been a time that it's easier now because you can literally pop in a paragraph from a paper or ask a question into ChatGPT, and it will give you a reasonable answer. Tomorrow, I'm giving talk on breast MRI and screening mammography, and it's been a decade since I learned it, and I actually had to go back and do a little bit of Google research. But you'd be surprised at how far you can get just by plugging a question into ChatGPT. So, um, as you go through your journey, you will have people above you that are mentoring you and be able to help you. Their most limited resource is their time. So if you come across something and you don't know what D-dimer is and you wait a week to ask that question or try to understand it, you will be a week behind, right? And so the more that you can, pull yourself up by your bootstraps in a sense and take it upon yourself to learn that and then go ask clarifying questions will enable you to accelerate yourself. And the people that have left our lab that have true superpowers are the ones that have picked up enough of the domain expertise along the way and not just isolated in their computer science world waiting for somebody to sort of explain and spoon feed them the meaning of X, Y, and Z. So I just really want to, and this week, especially during the Datathon and throughout your careers, take that to heart and really try to make sure that you begin to understand some of these things because they're not complicated. There's a ton of volume, but I think if you put in a little bit of effort, you'll be able to pick up a lot of the concepts too.
So thank you again, Wes and Smith.